Good day, learners. Welcome to our physical sciences lesson. My name is Amenim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11s, today we are going to consolidate acids and bases. We've been doing acids and bases, I think now is the 4th week. So I think you are all aware that this is the longest topic. So hence we took almost 4 weeks to finish it. So today the focus actually is questions, exam type questions, the multiple choice questions, and also the structured questions. So the knowledge area, I think you still remember, is chemical change. And then what we are going to focus on today, we just consolidate, acids and bases. So, but from next week, we'll be focusing on redox reactions, right? What is important again, learners? So please make sure that you go through the examination guidelines and then check bullet by bullet if we have covered everything. But I think we have done that, so you can do that on your own or together with your teachers. Just go through the examination guidelines bullet by bullet. Check if we did everything under acids and bases, right? So we are going to start with the multiple choice questions, because remember, when it comes to our examination, our question 1, whether it's your paper 1 or your paper 2, physics or chemistry, question 1 always, it's multiple choice questions, 10 multiple choice questions. And part of those questions, when it comes to your chemistry paper 2, part of those questions will be questions on acids and bases, right? So there's a lot under acids and bases, learners. So actually it's very, very important to make sure that we cover everything under acids and bases. So we tried actually to do that, right? So multiple choice questions. So let's start with this one. Consider the equation below. We are having H3PO4 plus H2O to produce H2O. To produce H3O plus plus H2PO forward minus, right? So before maybe we focus on the questions, what is important here, one is to give the names of those substances in that reaction. We have H3PO4, which is what we call phosphoric acid. Phosphoric acid. Okay, we have this one, which is water, right? We have this is hydronium ion, right? So yeah, so hydronium ion, and then this one we have what can say this is dihydrogen phosphate ion, right? Because they can ask you about the names instead of giving asking about the chemical formulae, right? So you have phosphoric acid, which is H3PO4 plus water, which is H2O, to produce hydronium ion, which is H3O plus, and then plus H2PO4 minus, which is what we can call dihydrogen phosphate ion, right? So let's focus on the question. So the question here is but maybe before we look at the question, this is an acid, right? So they can say define an acid either according to Lorentz or define an acid according to Arrhenius. So those are some of the things that you need to know, right? So phosphoric acid, it's an acid. So according to Lorentz, what is an acid? It is a proton donor, right? And then what is a base? It is a proton acceptor. So this is an acid, right? And then this is going to be what? A base. So a phosphoric acid plus water, which is acting as a base here, right? So when you check this side, you can see that water here has gained what? A proton, right? So it has gained a proton to become what? The hydronium ion. So what gains a proton? That is what? A base, right? And you are aware that a base produces what? A conjugate what? Acid. So what is a conjugate acid? A conjugate acid, that is a substance that is formed after a base has gained what? A proton. So there's addition of a proton when it comes to what? When it comes to a conjugate what? Acid, right? So H3O plus becomes what? The conjugate what? Acid, right? So conjugate acid is a substance formed after a base has gained a proton, right? So there's addition of what? Of a hydrogen ion to what? To a base to form what? A conjugate what? Acid. Yeah? So this is phosphoric acid. It's an acid, right? So according to Laurel Bronsted, an acid is a proton donor. So this H3O PO4 has donated now a proton. Hence this side you see how many protons is 2 protons. So it has donated a proton to H2O to produce what? H3O plus, right? Then after this H3PO4 has donated a proton, then it becomes what? H2PO4 what? Minus, right? So you can see that the third proton is no longer there, right? It has been what? Donated. So this is an acid, and we are aware that an acid forms or produces what? A conjugate what? Base, right? It produces what? A conjugate what? Base, right? So that is how actually you need to analyze what? An equation, right? Or a chemical what? Equation, right? So you have H3PO4 plus H2O to produce H3O plus H2PO4 what? Minus. So H3PO4, it's an acid which will produce what? A conjugate base. So a conjugate base is formed after, you know, a proton has been removed from what? From an acid, right? So a conjugate base is formed after a proton has been what? Removed from what? From an acid. So there's a what? A removal of a proton when it comes to a conjugate what? Base. Then when it comes to a conjugate what? Acid, there's addition of what? Of a proton. That is very, very important, right? So which one of the following is the conjugate acid base pair? So let's look at the reaction, right? So you have your conjugate acid base pairs, right? So it's H3PO4 to produce what? The conjugate what? A base, which is what? H2PO4. So that PO4 what? Minus. So that is the first conjugate acid base pair, right? Then the second one, right? So the second one would be what? H2O, right? To form what? H3O plus. So this is conjugate acid base pair 1, and then sorry about that, this is conjugate acid base pair 2, right? So let's look at the first one, the first option. So these are the conjugate acid base pairs. So this is the correct answer because B, this is an acid, right? So an acid will produce what? A conjugate what? Base. So it produces a conjugate base after we have removed what? A proton. So after the proton has been removed, it can't be H2O that will be formed, right? So this is incorrect. It can't be the conjugate what? Acid base pairs of each other, right? Then H3PO4 to produce H3O plus, again it cannot be, you know, so that option cannot be the correct option. Then H3O and what? An H2PO4 minus, again these two cannot be the conjugate acid base pairs. So but what is important there, this is actually how you should analyze what that chemical what equation. You must be able to tell that this is an acid, this is a base, this is a conjugate acid, this is a conjugate what? A conjugate base. So that you'll be able to answer questions on conjugate acid base what? Base pairs, right? So I hope you understood this one. Then if you have questions, then you'll ask questions and we can interact. So let's look at the second one. That is your 1.2. So sulfuric acid, right? So sulfuric acid, an acid is a proton donor, right? Or a substance that produces hydrogen ions or hydronium ions in aqueous water solution. That is according to Arrhenius, right? So an sulfuric acid ionizes in water according to the following equation. Then another thing, instead of just looking at those two equations there, one of the things that they can ask you is that it's sulfuric acid a strong acid or a weak acid, right? So you must be able to tell that it is a strong acid, because you already know the common strong acids, your sulfuric acid, your nitric acid, and also your hydrochloric acid. So those are strong acids. So sulfuric acid is a strong acid, and they will ask you, why are you saying sulfuric acid is a strong acid? There you need to give us the definition of a strong acid. So it ionizes completely in water to produce high concentration of hydronium ions. So it ionizes completely in water to form high concentration of hydronium ions. That is why it is a strong acid. So if they can ask you about its Ka value, the equilibrium constant value, or equilibrium constant of an acid value, then we are expecting the Ka of this strong acid to be greater than 1, because it is a strong acid. All right. Then if they talk of the concentration of hydronium ions, so there's a high concentration of hydronium ions here. Why am I saying there's a high concentration of hydronium ions? It's because it ionizes completely in water, and if it ionizes completely in water, it forms high concentration of hydronium ions. So those are some of the things that they can ask here. Maybe just when we do these questions, there's a lot that we're going to look at, not just looking at the questions or those options, you know. So there's a lot that I'm going to add based on the statements given, right? So the first equation there, we're having sulfuric acid, right? So sulfuric acid it's a strong acid. So all of us, we know that. So it's a strong acid. So it ionizes completely in water to produce or to form high concentration of hydronium ions. So if this is an acid, like it or not, this one is going to be a base, right? So this one is going to be a base. Water is going to be a base. Okay. Then this one, strong acid. Remember, strong acid, or an acid is a proton donor, so it's going to donate a proton. So after it has donated a proton, right, or after a proton has been removed, it forms a conjugate. So it forms a conjugate a base, right? So a conjugate base is formed after the removal of a proton from an acid. So after a proton has been removed from an acid, then what will be formed, or the substance that will be formed, it is going to be the conjugate base. So if this is the base, this one would be the conjugate acid. Okay, so conjugate acid is formed after an addition of a proton to a base. Then that is going to be the conjugate acid. Another thing that is very, very important here, learners, you are having a strong acid, right? So a strong acid produces a weak conjugate base, right? So this HSO4 minus, it's a weak conjugate base. So a strong acid produces a weak conjugate base. A strong base produces a weak conjugate acid, right? Then if we are having a weak acid, right, a weak acid will produce a strong conjugate base, and then a weak base will produce a strong conjugate acid. So those are some of the things that you need to know under conjugate acid base pairs, right? Then already you know that HSO4 minus, it is an acid, so it is a base. Then let's check here, right? So here you can see in the first equation, it's acting as as a base. But let's check in the second equation. You had HSO4 minus, there was a proton before, right, or on the side of the reactants, but on the side of the product, that proton is no longer there, right? So this becomes the conjugate. This becomes the conjugate base, because why am I saying the conjugate base? Conjugate base is formed after a proton has been removed from what? From an acid. So this is going to be what? An acid, right? So this is going to be what? An acid, and then this one is going to be what? A base, and this is going to be what? The conjugate what? Acid. So I hope we are together here, learners, right? So if you check when it comes to these two equations, right, you are having HSO4 minus, you are also having HSO4 what? Minus, right? We are having H2O. Even in the next equation, you are having what? H2O. But when you look at H2O in the first equation is acting as a base, and then also in the second equation is acting as what? As a base, right? So you can't say H2O in this case, it is the ampholyte. Remember, the ampholyte, that is a substance that can either act as an acid or what? Or a base. But we know that water is an ampholyte. But in these two reactions, is it acting as an ampholyte? No. Why am I saying that? It's because in the first equation is acting as a base. Even in the second equation is also acting as what? As a base, right? Then HSO4 minus is also an ampholyte, right? So an ampholyte is a substance that can either act as an acid or what? Or a base, depending on what it is reacting with, right? So let's check in the first equation. So HSO4 minus, which is hydrogen sulfate ion, right? Hydrogen sulfate ion, right? So you're having sulfuric acid, you're having water, you're having hydronium ion, we are having hydrogen sulfate what? Ion. In the second equation, we are having hydrogen sulfate ion, we are having water, we are having hydronium ion, and this is a sulfate what? Ion, right? So in the first equation, we are having HSO4 minus, which is the sulfate ion. Even here, it is what? We are also having the sulfate what? Ion. So in the first equation is acting as a base, but in the second equation is acting as what? As an acid. So which means that for these two reactions, our ampholyte is not water, but our ampholyte is hydrogen sulfate what? Ion. Our ampholyte is hydrogen sulfate what? Ion. Why am I saying it's a hydrogen sulfate ion? First thing, for you to be to identify that, this is what we have to do. Identify acid, identify base, conjugate acid, conjugate base, right? Then from there, you'll be able to tell whether the substance in those two equations is acting as an ampholyte or not, all right? So let's look at the question here. Consider the following statements regarding the ionization above. What is ionization, right? So again, you should know what is ionization. So ionization, it's a reaction it is what? A reaction where a covalent molecule or a covalent compound, it's it forms what? Ions in what? In water, right? So that is ionization. That is the reaction where the covalent what? Ions, sorry, covalent compound forms ions in what? In water. So for example, your H2SO4, it's a covalent compound, right? So when it is dissolved in water, it will form what? Ions. So sulfuric acid is a covalent compound, right? So when it is dissolved in water, for example, here we are dissolving it in what? In water. It forms what? It forms ions, your hydronium ions, and what? And hydrogen sulfate what? Ions. So that is ionization. It's a reaction where a covalent compound forms ion in what? In water, right? So we have Roman figure 1. Consider the following statements regarding the ionization above, right? H2O acts as a base in both reactions, right? Is it correct or not? Yes, it is correct. It is acting as what? As a base in both what? Reactions, right? Hydrogen sulfate ion acts as an ampholyte. Is it true? Yes, it is acting as an ampholyte. In the first equation, it is acting as a base, but in the second equation, it is acting as what? As an acid. So a substance that can either act as a base or an acid, we call it what? The ampholyte. So it is also what? Correct. Ne? Then the third option there, or the Roman figure 3, sulfate ion is the conjugate base of sulfuric acid, right? Sulfate ion is the conjugate base of what? Of sulfuric acid. So for the two equations, right? So if they say sulfate ion is the conjugate base of, yes, we understand that sulfate ion, look at the reaction 2. They are talking about the sulfate ion, right? So the sulfate ion is in reaction 2, right, or equation 2. So, and this sulfate ion here is the conjugate base, right? But is the conjugate base of which acid? Hydrogen sulfate ion, not sulfuric acid. What is the conjugate base of this sulfuric acid? Is hydrogen sulfate ion. I hope you are following, right? The focus here is a sulfate ion, right? I'm having a sulfate ion in the second equation, right? So they're saying the sulfate ion is the conjugate base. Yes, it is the conjugate base, right? But is the conjugate base of which acid? The acid is hydrogen sulfate ion, right? Then Roman figure 3 cannot be correct for these two reactions, right? So sulfate ion actually is the conjugate base of hydrogen sulfate ion, not sulfuric acid. Okay, so Roman figure 3 it's out. So we are focusing on what? Roman figure 1 and Roman figure 2. So we want an option that will talk to, or that will have those two Roman figures, or those two statements, which is Roman figure 1 and Roman figure 2. So if you say A only, it can be. So our option must accommodate both statements, right? Which is a 1 and 2. So our correct answer here, learners, will be B. It can't be D because D includes what? Roman figure 3. It can't be C because C also includes what? Roman figure 3. So Roman figure 3 is not correct for these two equations, right? So I hope you are fine, learners, and I hope you can see how we answer multiple choice questions. We don't just say, okay, it's 1.2, I think, right? The correct option will be D, or the correct option will be A, or the correct option will be what? Will be C. So you have to analyze, you know, that question, so that you'll be able to answer it. All right. So this is how actually you need to analyze it. So the way we have analyzed it, it shows that the correct answer here will be what? Will be B. But if you just look at the two reactions and then they say sulfate, hydrogen sulfate ion is an ampholyte, then you are only thinking of water, then we are in trouble, which means that you won't get that question correct. So it's very, very important to when you're given a statement, read with understanding, analyze that question, that statement, so that you'll be able to answer what? The questions, right? Let's look at Roman figure 3. I hope, learners, we are still together. Or let's look at 1.3. Right, so it's still on acids and bases. We are focusing on the multiple choice questions. I hope, learners, we can see that when it comes to multiple choice questions, they're not just easy. I think you've seen a lot of work that I've done when it comes to my 1.1, my 1.2, right? So you have to do the same, learners, for you to be able to get that 2 marks. You have to work for that 2 marks. Don't just say, because 1.1 was A, it means that it might happen that 1.2 is also A. No, you don't do that, okay? If you're going to do that, you can get 0 out of 20 marks. And if you get 0 for multiple choice questions, there's no way, or the probability of you passing, or the chances of you passing, they're very, very slim, right? So let's look at your 1.3. Your 1.3, we are given the nitric acid, right? Nitric acid, yes, it's an acid, a proton donor, or a substance that what forms hydronium ions in aqueous solution. That is according to Arrhenius. But again, is nitric acid a strong acid or a weak acid? So you must be able to tell us that nitric acid is a what? Is a strong what acid? Because you already know the common strong acids, right? We already know the common strong what? Acids, right? So if it is a strong acid, right, one, you know that it ionizes completely in water to form what? High concentration of hydronium ions, right? So if there is high concentration of hydronium ions, right, one, okay, it's an acid. Let's start there. It's an acid, okay? We're expecting its pH, right? Its pH to be what? To be less than 7, right? Okay, so we are expecting what here? High concentration of what? Of hydronium what? Ions. right? Then we are given ethanoic acid. You know ethanoic acid is a weak acid. They will ask you, why ethanoic acid is a weak acid? It ionizes incompletely in water to form low concentration of hydronium ions, right? So concentration of hydronium ions here, they're very, very low, right? Okay, so we are having ethanoic acid here, learners. Ethanoic acid is a weak acid. It ionizes incompletely in water to form low concentration of hydronium ions. Even here, the pH, we are expecting the pH to be less than 7. It's an acid, so pH of acids is always less than 7, or the pH of acidic solutions is always less than 7. But another thing which is important here, learners, is that when it comes to strong acids, the pH of strong acids is very, very low, right? The pH of strong acids is very, very low. So remember, when it comes to strong acids, right? So there is high concentration of hydronium ions. Remember, as a concentration of hydronium ions increases, pH of the solution decreases, right? As concentration of hydronium ions increases, pH of the solution decreases. So the pH of nitric acid, we are expecting it to be around or between 0 and 2.5, right? Then when it comes to ethanoic acid, remember here there is low concentration of hydronium ions. Oh, you wanted me to repeat the meaning of ionization, right? So there's ionization, there's dissociation, right? So when you talk of ionization, covalent compounds, they ionize, right, when they're dissolved in water, right? And then ionic substances or ionic compounds, they dissociate when they are dissolved in water, right? So a covalent compound, for example, so I'm trying to answer your question, my learner. So you are having HCl. HCl is a covalent compound, right? Why am I saying it's a covalent compound, right? So remember, when it comes to a covalent compound, right, atoms are held together by covalent bonds, right? So here, and you still remember that maybe from grade 10, that a covalent bond is formed between two nonmetals. So hydrogen is a nonmetal, chlorine is also a nonmetal. So between hydrogen and chlorine, the bond, or the chemical bond, there is it's a covalent bond. Hence, the substance will be a covalent compound, right? So covalent compounds, right? They form ions when they're dissolved in water. So here I will have HCl, then plus H2O. Then what am I going to have here? H3O plus what? Plus Cl minus. So they only form ions when they're dissolved in water. So but on their own, they don't have ions. They will only form ions when they're dissolved in water. So covalent compounds like your HCl, your nitric acid, your ethanoic acid is also a covalent compound, right? So when they're dissolved in water, they form ions, right? Then, so we say they They ionize. They ionize, right? Then ionic substances, for example, NaCl is an ionic substance. Why am I saying NaCl is an ionic substance? Remember, these two atoms, sodium atom and the chlorine atom, they're held together by By an ionic bond. So remember, in grade 10, you know that an ionic bond is formed between a metal and a non-metal. So between a non-metal and a metal, right? So a bond will be ionic, right? So if there's an ionic bond here, then the compound becomes an ionic compound. So in an ionic compound, already ions are there, right? In an ionic compound, already ions are there. But in a covalent compound, ions are not there, right? But when those covalent compounds are dissolved in water, they will form ions. I hope it's making sense, right? But when it comes to an ionic compound, the ions are already there, right? but they are not free to do what? To move, right? They will be only free when this compound or the ionic compound is dissolved in what? In water. When it is dissolved in water, then these ions will be what now? Will be free. So, and that is what we call dissociation. So dissociation, that is the process whereby ionic compounds break into ions in what? In water, right? So ions are already there, but they are not free to do what? To move. Then when this compound, the ionic compound, is dissolved in what? In water, it will form what? It will break into what? Into those ions. So that is dissociation. So ionization is for covalent compounds, and then dissociation is for ionic compounds. So ionic compounds, they dissociate in what? In water. They break into ions in what? In water. So already, right, ions, they were already there in that solid form, right? But now they were not free to do what? To move. But now when this is dissolved in water, then ions will be what? Will be free to do what? To move, and we'll be able to see those what? Those ions. So dissociation is for ionic compounds, and then ionization is for covalent what? Compounds. So covalent compounds, they ionize. They form ions when they're dissolved in what? In water. But ionic substances, they break into ions when they're dissolved in what? In water. So they will break into ions when they're dissolved in what? In water. So please, learners, be careful when it comes to those two terms, né? Ionization, dissociation. Learners, that's the reason why when we define a weak base, we say a weak base ionize or dissociate. Why are we saying ionize? We are trying to accommodate, you know, weak bases that are ionic, right, and also weak bases that are covalent, right? For example, your ammonia is a covalent compound, right? So we can't say ammonia dissociate. Ammonia and ionize in water. Yes, it ionizes in what? In water, because it is a covalent what? Compound. So I hope it's making sense, right? So that's the reason why when you define a weak base, some weak bases, they are what? They are ionic, but some weak bases, they are what? They are covalent. For example, ammonia is a covalent compound, so we can't say ammonia, you know, dissociate. We have to say ammonia ionize. All right, so ionization is for covalent compounds, and then dissociation is for what? Is for ionic what? Compounds. So I hope it's making sense. So I've tried to explain ionization together with what? With dissociation, right? Okay, let's move. What we are having, a weak acid versus a strong acid. Your strong acid is nitric acid, and then your weak acid is ethanoic what? Acid. So what we know that acids, when they're dissolved in water, they form hydronium what? Ions, right? And then you are having nitric acid, which is a strong what? Acid, so it ionizes completely in water to form high concentration of what? Of hydronium ions. But when it comes to ethanoic acid, it ionizes incompletely in water to form low concentration of hydronium what? Ions, right? So there's low concentration of hydronium ions when it comes to ethanoic acid. There's high concentration of hydronium ions when it comes to a solution of nitric acid, all right? Then pH for both, we're expecting it to be less than 7, but it cannot be equal. Why am I saying it? The pH values cannot be equal. Remember, it is what? A weak acid versus what? A strong acid. So with a strong acid, there is high concentration of what? Of hydronium ions. We're expecting the pH to be very low. Hence, I said between 0 and what? And 2.5, right? Then when it comes to ethanoic acid, the concentration of hydronium ions is very low. So we're expecting the pH to be high, right? But still less than 7. Okay, to be high, but still less than what? Less than 7. So maybe we're expecting the pH here to be between what? 2 point what? What is this? 2.6 maybe to what? To 6 point what? To 6.9. That is for weak bases. I hope this is making sense, learners. These are acids. We're expecting the pH to be less than 7 for both. But when it comes to a strong acid, there is high concentration of hydronium ions, which makes the solution, the pH of the solution to be very low. Then when it comes to a ethanoic acid, which is a weak acid. Remember, it ionizes incompletely in order to produce low or to form low concentration of hydronium ions. So there's low concentration of hydronium ions in a solution of ethanoic acid. Then we're expecting the pH to be high, but still less than what? Less than 7, right? So those are some of the facts when it comes to these two acids, right? Weak versus what? Versus strong, right? Then now again, when it comes to the issue of electrical conductivity, all right? So what determines the conductivity here is the concentration of ions in the solution, right? Remember, when it comes to a nitric acid, it ionizes completely in water to form high concentration of hydronium ions. This other one, which is the ethanoic acid, a weak acid, ionizes incompletely in water to form low concentration of hydronium ions, right? So what determines the concentration is, the conductivity is the concentration of ions in the solution, right? So if there is high concentration of ions in the solution, the conductivity is also going to be high. So what am I trying to say to you is that as concentration of ions in the solution increases, even the conductivity of the solution will increase. If there is high concentration of ions in the solution, there will be high conductivity or electrical conductivity of that solution. But if there is low concentration of ions in the solution, there will be low electrical conductivity. All right. So what determines the conductivity is the concentration of ions in the solution. So as the concentration of ions in the solution increases, the conductivity or the electrical conductivity of that solution will also increase. But as you decrease, or if the concentration of ions in the solution is low, even the conductivity is also going to be low. Now let's look at these two acids. All right. Then we have strong versus weak. Strong, high concentration of hydronium ions in the solution, right? Obviously expecting the conductivity of nitric acid to be high, right? Then when it comes to ethanoic acid, there's low concentration of hydronium ions in that solution. We are expecting the conductivity also going to be to be low, right? So that is what we need to understand. So when it comes to Roman figure 1, they have different pH values. That is true. We're expecting them to have different pH values. Yes, the pH should be less than 7, but the pH cannot be the same. Why am I saying the pH cannot be the same? It's because it's a strong acid versus a weak acid. Strong acid, high concentration of hydronium ions in that solution, which makes the pH to be low, right? And then weak acid, low concentration of hydronium ions in that solution, which makes the pH to be high, but still less than what? Less than 7. So I agree with I accept Roman figure 1. They have different pH values. All right. Both have the same electrical conductivity. I disagree. I hope also at home, wherever you're seated, right, you also disagree with Roman figure 2. How come they can have the same electrical conductivity, while the other one has forms high concentration of hydronium ions, the other one forms low concentration of hydronium ions, right? Remember, what determines the conductivity? Conductivity actually is based on what affects the conductivity is the concentration of ions in the solution, right? So there's high concentration of hydronium ions in nitric acid solution. There's low concentration of hydronium ions in ethanoic acid solution. So obviously the conductivity can never be, or it will not be the same. It's a weak acid versus a strong acid. So Roman figure 2 is out. Okay. Then let's look at Roman figure 3. I hope you understand why Roman figure 2 is out. Why they cannot have the same electrical conductivity. Start by identifying whether the acid is strong or weak. It's where you have to start. So with acids and bases, there's a lot that you need to do for you to be able to answer these questions, right? So in most cases here, you won't get, those low order questions, right? So for example, this one you have to analyze. You need to take your time for you to be able to get the correct answer here, right? So start by identifying whether the acid is strong or weak, right? What is the meaning of an acid being strong, being weak, right? then how does that concentration of hydronium ions relate to pH values, relate to what? To electrical what? Conductivity, right? Roman figure 3, both solutions require the same number of moles of potassium hydroxide for complete what? Neutralization, right? So now what is important here for you to prove that this is true? You need to write the reactions, okay? So the reaction of nitric acid, so I'm having nitric acid plus what? KOH. So nitric acid plus KOH, what will be formed here? It will be what? KNO3, potassium nitrate plus what? Plus H2O, okay? Then is the equation balanced? 1 hydrogen, or 1, 2, even this side is 2. Nitrogen is 1, 2, O3 plus 1, which is 4 oxygen atoms. Even this side is 4 oxygen what? Atoms. And then potassium 1, 1, right? So the equation is what? Is balanced, right? So what is the ratio? This is very, very important. So for you to understand this question. What is the ratio for the first equation? What is the ratio of nitric acid to potassium hydroxide? Ratio is 1 is to what? Is to 1. Those are number of moles. Ne? So let's look at the second one now. Ethanoic acid. Ne? Ethanoic acid. So here I was explaining ionization. Ne? Right. So now I'm having ethanoic what? Acid plus what? Potassium hydroxide. What will be produced here is potassium acetate or ethanoate, which is CH3COOK plus H2O. Okay, so let's check if the equation is balanced. I'm having how many carbons? 1, 2. So yes, how many carbons? 1, 2. Even this side, how many carbons? 1, 2, right? So carbon atoms are balanced. Then how many hydrogens is 3 plus 1, which is 4 plus 1, which is going to be what? 5. Ne? Okay, so it's 3 plus 1 plus 1, which is what? 5. It's 3 plus 2, which is also what? 5. All right. Then let's move to oxygen atoms. 1, 2, 3. This side 1, 2, 3. All right. Then potassium atoms 1. Even this other side is also what? 1. So the equation is what? Is balanced, right? What is the ratio? What is the ratio of acid to a base? Ratio of ethanoic acid right, so ratio of ethanoic acid, sorry about that, to potassium hydroxide. Again, ratio here is 1 is to 1, right? Right. So the ratio of ethanoic acid to potassium hydroxide is also 1 is to 1. Now let's go back to that statement, okay? Both solutions require the same number of moles of potassium hydroxide for complete what? Neutralization. So I'm looking at the number of moles. For the first one, where you have nitric acid plus potassium hydroxide, the ratio is 1 is to 1. Nitric acid to potassium hydroxide is 1 is to 1, right? And then when it comes to the second one is ethanoic acid plus potassium hydroxide, the ratio of ethanoic acid to potassium hydroxide is also what? 1 is to 1. So which means that both solutions require the same number of moles of potassium hydroxide for complete what? Neutralization. So Roman figure 1 is correct. Roman figure 3 is also what? Correct. But what is not correct here, or what is incorrect here for these two acids, it's Roman figure what? 2. So we are looking for an option where we are having Roman figure 1 and Roman figure 3, right? So A will be out because it only talks to, you know, Roman figure 1. And then 2 or option B will be out because they've included Roman figure 2 And Roman figure 2 says both they have the same electrical what conductivity. Already we have explained that it cannot be, right? Then 1 and 3 is the correct one, right? So 1 and 3 is the correct one, but 2 and 3, 2 is here, 2 is out, right? But Roman figure 3 we know it's what is correct, né? So hence this one will be, it won't be the correct what option. So I hope, learners, you have seen how we have analyzed the equation, all right, or the statement, for us to be able to get what the correct answer. So it's not just, you know, look at the statement and then just take any answer. There's something that you need to do there. You have to analyze that statement, and then so that you can get what the correct answer. 1.4, which is going to be our last question on multiple choice questions. Right, so according to Laurie-Bronsted what theory? So Laurie-Bronsted theory, right, what is an acid? Proton donor. What is a base? A proton what? Acceptor. Right? Then a conjugate base, okay, is formed when? When is the conjugate base formed? What forms a conjugate base? What forms a conjugate base is an acid, right? For example, I'm just giving you an example. You have an acid, right? Then acid is a proton donor. We remove a proton here. When this proton is removed, what will be left is Cl minus. Then the Cl minus becomes what? This is an acid. And then this is what is going to be what? The conjugate what? The conjugate what? Base. So you can see that a conjugate base is formed after a proton has been what? Removed from an acid. Ne? A conjugate acid base actually it's formed after a proton has been removed from what? From an acid. Ne? Now let's look at the base. This is the base. A base will form what? A conjugate what? Acid. So we add what here? We are going to add what here? A proton to this ammonia to form what? Ammonium what? Ion. Okay? And then this ammonium ion becomes what? The conjugate what? Acid. Right? So a conjugate acid actually is formed after addition of a proton to a base. Ne? So here there is what? Addition of a proton to what? To a base. This one, removal of proton or H plus from an acid. That is the conjugate base. Is formed after a proton has been removed from an acid. That is the conjugate base. Ne? Then a conjugate acid is formed after we have added a proton to what? To a base. I hope it's making sense. Right. Now, I will look into that question. Let me finish 1.4. Right. So a conjugate base is formed when an acid. So conjugate base is formed after we have removed a proton from what? From an acid. That is the conjugate base. You can see Cl minus is our conjugate base. We have removed a proton from an acid. Ne? Proton added. We can never add a proton to an acid. Remember, an acid should donate. So this statement is wrong. Proton is added to an acid. So we cannot add a proton to an acid because according to Laurie-Bronsted, an acid is the proton donor. We can only remove a proton from what? From an acid, not add it. We only add a proton to what? To a base, right? So this is out, completely out. Can never have something like this when it comes to Laurie-Bronsted theory, all right? Electron is added to the acid. So here we are talking about what? Acid-base reactions. So the driving force for acid-base reactions, it's a proton, ne? Or it's transfer of what? Of protons, not of electrons. We talk of electrons when it comes to redox reactions, which is what we are going to focus on next week. So electron is added to an acid? No, right? So we talk of electron transfer when it comes to redox reactions. So that is the driving force for redox reactions. And then the driving force for acid-base reactions, it's what? It's transfer of what? Of protons. So if we don't talk of electrons here, but we talk of what? Of protons. So this one is also out. Proton is removed from the acid. Yes, we do. We remove a proton from an acid according to Laurie-Bronsted. We don't add proton to an acid. Okay, so this one, it's a correct word statement, right? But does it answer the question? Conjugate base. A conjugate base is formed after we have removed what? A proton. After I've removed a proton from what? From an acid. Yes, so this one is correct. Electron is for redox reactions. So D is also what? Incorrect. So C is the correct answer. Learners, conjugate base is formed after we have removed a proton from an acid. Conjugate acid is formed after we have added a proton to what? To a base. That is very, very important, right? So these are the solutions. Right, so there's a question here, learners. Can the substance dissociate or ionize without the presence of water? Because he mentioned that water, but what if water is not present and another liquid is involved? Ne? Right, so when it comes to dissociation, ionization, the solvent should be water. So there's no way that a substance can dissociate or ionize without water, right? So the solvent should be what? Water. So I think we have answered your question. The solvent should be water. So there's no way that it will dissociate using a different solvent. The solvent should be what? Water. Hence, when we talk of ionization, right, it's when, obvious, it should be a reaction where now a covalent compound forms ions in what? In water, right? Then a dissociation, an ionic compound break into ions where? In water. So dissociation, ionization, the solvent should be what? Should be water. Or an ionic substance is dissolved in water. A covalent compound is dissolved in what? In water. So the solvent should be what? Should be water, right? So if it's another liquid, then no dissociation, no ionization. So ionization, the solvent should be water, right? I hope I've answered your question, right? Then structured questions. So we're looking at the multiple choice questions. Now let's look at the structured what questions, right? So learners prepare a solution of known concentration, right, by dissolving 2 grams pure sodium hydroxide crystals in water in 250 cubic centimeter volumetric watt flask. Last week we were looking at how to prepare a standard solution, how to perform titration, right? And we even mentioned, you know, the apparatus that are needed for preparing a standard solution and also for titration experiment, right? So volumetric flask, this one, remember, it measures what? The volume, right, of a solution. Okay, so we use it when it comes to preparation of a standard what? Solution, right? And what is a standard solution? A standard solution, remember, it's a solution with a known what? Concentration. So let us prepare a solution of known concentration. Obviously you expect this is what? A standard solution. Okay, by dissolving 2 grams pure sodium hydroxide crystals, right? So we are talking about sodium hydroxide crystals. And sodium hydroxide, learners, it's an ionic what? Compound, right? Here, ions are already present, but they're in a crystal, so they're not free to move. So if they're not free to move, so that substance cannot conduct what? Electricity. Ne? Now we are dissolving it in what? In water. So what is that process called when you are dissolving the crystals of sodium hydroxide in water? That process is going to be what? Dissociation. Okay? So you can see the solvent is still what? There? Water. So you are dissolving it in what? In water, not into another what? Substance. So this process where we dissolve this sodium hydroxide crystals in water, the process is going to be what? Dissociation. So hence we say dissociation is a process whereby ionic compound break into ions in what? In water, right? Or in aqueous what? Solution, right? So here you have the mass of sodium hydroxide, you have the volume of the solution of sodium what? Hydroxide. All right, so 7.1, write down the term for the underlined phrase, right? already we have answered that. A solution of known concentration, we call that solution a standard what? Solution. Okay. Then 7.2, there are calculations there. They want us to calculate the concentration of sodium hydroxide what? Solution. Okay. There are two equations that we can use to calculate the concentration. Okay. There are two equations that we can use to calculate what? The concentration. Where are these equations coming from? Not from heaven, but from the data sheet. So you copy the equation as it is from the data sheet. So I'm having C equals to what here? N over V. I'm also having C equals to mass over molar mass times what? Times volume. All right. So there are two equations that we can use to calculate the concentration of a solution. Right. So, right. So if we want the concentration here using this equation, where should we start? We have to start by getting the number of moles of that a substance. Okay. And then already we have the volume. So let's start by getting the number of moles. How can we calculate the number of moles? There's different equations that we can use to calculate the number of moles. We can calculate number of moles using mass over molar mass, right? You can calculate the number of moles using the equation CV from C equals to N over V. You can use N over what? Over NA. If you're given the number of particles, right? You can use V over what? Over Vm, right? So for gases at standard temperature and what? And pressure. Okay, so these are the equations that we can use to calculate what? The number of moles. V over Vm, but V over Vm, remember, it's number of moles of a gas at STP. M over M, which is mass over molar mass, all right, if you're given the mass, and then CV if you're given the concentration and the volume, N over NA, which you're given if you're given the number of particles, and then using what? Also the Avogadro's number, all right. But here, if you check in on that statement, you are given the mass, right, and we can get the molar mass of that substance using the periodic table. So let's use N equals to mass over molar mass. All right. So the mass, it's what? They said it's 2. Okay. The molar mass of sodium hydroxide. Molar mass of sodium hydroxide goes straight to the periodic table. So we are looking for the molar mass of sodium hydroxide. Sodium, the relative atomic mass of sodium is 23, and then oxygen is 16, right? And then hydrogen is what? It's 1. So what is 23? Press your calculator. 23 plus 16 plus 1. So I'm having 40 grams per mole. Right? So here I will have to divide by what? By 40. So what is 2 divided by 40? So 2 divided by 40, I'm getting 0.05. And learners, you are not supposed to round off this answer. Remember, this is not your final answer. Your final answer should be the concentration of the solution of sodium hydroxide. Okay, now I have the number of moles. So now if I have number of moles, I can go straight to the equation C equals to N over V. N is 0.05 and the volume is 250 cubic centimeters. That is the volume of the volumetric flask that was used to prepare that solution of sodium hydroxide. Ne? So if it's 250 cubic centimeters, when it comes to this equation of C equals to N over V, we want V in cubic decimeters, right? So you have to convert cubic centimeters to cubic decimeters. How? You divide that 250 by 1000, right? So it will be 250 divided by 1000. So 250 divided by 1000, I'm getting 0.25, right? So 0.25. So what is 0.05 divided by 0.25? That will be the concentration, 0.2 mole per cubic decimeter. That will be the concentration of what? Of sodium hydroxide what? Solution, right? Or you can just go straight to the equation C equals to what? Mass over molar mass times volume. What is the mass is 2, molar mass is 40, the volume is what? 0.25. Where am I getting this 0.25 from? From 250 dividing that by what? 1000, because I want my volume to be in cubic decimeters, not cubic what? Centimeters, right? So then the answer should be the same, which is 0.2 mole per cubic what? Decimeter, right? So that is how we were supposed to calculate the concentration of sodium hydroxide what? Solution. So the concentration of this solution is 0.2 mole per cubic decimeter, right? Another thing that they can ask here is that is this solution of sodium hydroxide concentrated or dilute, right? So is it concentrated or dilute? Then this solution of sodium hydroxide is what? Is dilute. Why am I saying it's dilute? Is because its concentration is less than 1. That is very, very important. So this solution of sodium hydroxide is dilute, right? Why is it dilute? Because its concentration is less than what? 1. Unless if the concentration was greater than 1, then we're going to say this solution of sodium hydroxide is concentrated, but it's dilute in this case. Why are we concluding it as being dilute? It's because its concentration is less than 1. You can see it's 0.2, which is less than 1, right? Then they also want us to calculate the pH of this solution, right? So the pH of this solution, how do we calculate pH? Now we are calculating the pH. So the pH from the data sheet is negative log concentration of hydronium what? Ions. So can you see that for us to calculate the concentration, we need, the pH, we need the concentration of hydronium ions. But when it comes to a solution of sodium hydroxide, we won't get the concentration of hydronium ions. We'll only get the concentration of hydroxide what? Ions. Remember, a base, according to Arrhenius, right? So it's a substance that produces hydroxide ions in aqueous what? Solution. So we'll only get the concentration of hydroxide ions, right, when it comes to that solution of sodium hydroxide. So let's get the concentration of hydroxide ions. So NaOH to hydroxide ions, the ratio is 1:1. So in one molecule of sodium hydroxide, how many hydroxide ions are there? It's 1, right? So hence the ratio is what? It's 1:1. So if the concentration is 0.2, even the concentration of hydroxide ions will be 0.2 mole per cubic what? Decimeter. We have the concentration of hydroxide ions now, right? So this is the concentration of hydroxide what? Ions. So but according to the equation, we need the concentration of hydronium what? Ions. So what are we supposed to do here? We go straight to Kw, right? So Kw, it's concentration of hydronium ions, multiply that by concentration of hydroxide ions. This will be equals to 1 times 10 to the power negative 14 at 25 degrees Celsius, okay? So I'm looking for what? Concentration of what now? Of hydronium ions. So concentration of hydronium ions will be 1 times 10 to the power negative 14 divided by concentration of hydroxide ions, which is what? 0.2. Okay, so then now after getting the concentration of hydronium ions, I will be able to calculate what now? The pH. So now let me calculate the pH, which is negative log concentration of what? Of hydronium what? Ions, which is negative log. What is the concentration? Is 1 times 10 to the power negative 14 divided by 0.2. So what's your answer here? And this pH, we are expecting it to be greater than 7. Why should be greater than 7? Because we are talking about a base here. pH of bases should be greater than what? 7. So here I'm having what? Negative what? Log. Negative log concentration of what? 1 times 10 to the power negative 14 divided by what? 0.2. Okay. So here I'm getting 12.3. Okay. So that is the the pH of sodium hydroxide solution. Yes, I'm expecting the pH to be greater than 7, but still less than what? Less than 14. So if it happens that you get a negative pH or pH that is greater than 14, then there's something wrong. So you need to go back, right? So that is the pH of that solution. So I think we have seen how we calculate what pH. Remember, these are questions. We have done this pH as a subtopic. So now remember, we are focusing on what the whole of acids and bases, where they can ask whatever they want to ask, right? So which means that here we have to know everything under acids and bases. Now let's look at another question. Another question here. Okay, we have calculated what the concentration of sodium hydroxide solution. We got 0.2 mole per cubic decimeter. We have calculated the pH. We got 12.3 or 12.3 because pH has no units, right? Now learners, again, you should read this with understanding. We can see it's 8 marks, right? So here we are not answering the marks, but we are answering the question. So, and for you to be able to get these marks, please read the statement with understanding, right? This also applies to grade 12 because these acids and bases that we are doing here, even the grade 12s are doing the same thing. So this is very also relevant for our grade 12s that are going to write physical sciences or chemistry on the 11th of November. Okay, right. So the learners now react 1.5 grams of pure calcium carbonate with 50 cubic centimeters dilute hydrochloric acid of unknown what concentration. All right, we don't know the concentration of this dilute acid. Okay, right, but we know its volume, right? So for this acid dilute, so if it's dilute, I know my answer. If they can ask me to calculate the concentration of this dilute acid, right, I should know that the concentration should never be greater than 1. My answer should not be greater than 1. It should be less than 1 because I'm told that this acid is dilute. So it's dilute acid, which is the HCl. So what are we having for HCl? Volume. It's what? 50 cubic what? Decimeters. No, it's not per cubic, but it's 50 cubic decimeters. We don't know its initial what? Concentration. All right. What else is given? We are given what? Calcium carbonate solution, in a solid form. We have 1.5, the mass of it is 1.5 grams. All right. Then, that is for the first equation. Hydrochloric acid plus calcium carbonate to produce calcium chloride, carbon dioxide, and water. Right. Then, the excess, this is very, very important. The excess hydrochloric acid is neutralized with 25 cubic centimeters of sodium hydroxide solution that they prepared. I repeat, the excess hydrochloric acid is neutralized with 25 cubic centimeters of the sodium hydroxide solution they prepared. So the sodium hydroxide solution that they prepared, its concentration was 0.2, if you still remember. Then what is the volume that neutralizes this excess hydrochloric acid? It's what? It's 25 cubic what? Decimeters, right? So the excess hydrochloric acid is neutralized with 25 cubic centimeters of the solution or sodium hydroxide solution that they prepared. Then these are the balanced what? These are the balanced equation. The second equation, hydrochloric acid, sodium plus sodium hydroxide to produce sodium chloride plus what? Plus water. Right. So where are we supposed to start here? They want us, okay, to calculate the initial concentration of the dilute hydrochloric what? Acid. They need us to calculate the concentration or the initial concentration of the dilute hydrochloric acid. So here we have to work backwards, right? So what is happening here in this reaction? You are given what? The number of, sorry, what is this? The concentration and the volume, right? So if you're given the concentration and the volume, you can calculate the number of moles of 8, right? So let's calculate the number of moles of sodium hydroxide that was used to neutralize the excess hydrochloric acid. Okay, that was used to neutralize what? The excess hydrochloric acid. Ne? Okay, so the number of moles of sodium hydroxide, we are given what? Concentration and volume. So it's CV from C equals to N over V, right? So the concentration is 0.2, then times 0.025. Why 0.025? It's because the volume that neutralizes hydrochloric acid is what? It's 25 cubic centimeters. Ne? So I'm having 0.2 times 0.025. So here the number of moles is 0.005 mole. Ne? So these are number of moles of sodium hydroxide that are needed to neutralize the excess hydrochloric acid. Ne? So from here we can even get the number of moles of excess hydrochloric acid. The number of moles of excess hydrochloric acid. Ne? So ratio HCl to sodium hydroxide ratio is 1 is to what? Is to 1. Ne? So the number of moles of HCl in excess will be 0.05 mole per cubic mole. Actually, these are number of of moles, right? Then we have the number of moles of excess. Now let's go back, right? So let's read the statement again. Okay, the learners now react 1.5 grams of calcium carbonate, I hope you are following, with 50 cubic centimeters dilute hydrochloric acid of unknown concentration. Okay, now from that statement and the statement after the full stop, the excess. So we are told that this actually is in is in excess. Okay, the hydrochloric acid. So for calcium carbonate, we can also calculate the number of moles of calcium carbonate. All right. So calcium carbonate, what is this? The mass is 1.5. Then we have the molar mass. All right. So number of moles of calcium carbonate, all right, equals to mass over molar mass. The mass is 1.5. The molar mass, calcium is 40 plus 12 plus 3 times 16, which is what? 100 grams per mole. Okay. So I'm getting that from the periodic table. 1.5 divided by what? 100. So the number of moles, it's 0.015 mole. So these are number of moles of what? These are number of moles of calcium carbonate. So I hope we are still together. Right. So these are a number of moles of calcium carbonate. Okay. Then from here, we can get the number of moles of what? The number of moles of hydrochloric acid, using mole ratio. So mole ratio, let's go back to that reaction. Sorry about that. So the mole ratio you can see is 2 is to what? Is to 1. Ne? So 2 is to 1. So calcium carbonate is to what? Hydrochloric acid. Ne? So ratio is 2 is to what? Is to 1. Right. So 2 for an acid and then 1 for what? For a base. Okay. Right. Then the number of moles 0.015, and then we don't know the number of moles of hydrochloric what? Acid. Ne? All right. Then the number of moles of hydrochloric acid will be 2 times 0.015, ne? Which is 0.03 mole, right? Then the initial number of moles of HCl will be 0.03 plus this number of moles, which is 0.05 mole. Okay, then we'll get the initial number of what? Of moles plus 0. Remember, we're looking for the initial concentration, ne? So it's 0.03 plus 0.05, ne? So the total number of moles, actually, the total number of moles of HCl is 0.08 what? Mole. That is the total number of moles of what? Of HCl. So if the total number of moles of HCl is 0.08, what will be the initial concentration now? Number of moles over what? Over volume. The number of moles, initial number of moles 0.08. Initial volume, right? The initial volume is what? They said is 50, which is going to be what? 0.05. Then what is 0.08 divided by 0.05? It's let me check here. It's 0.08 minus 0.03 divided by, right. So here we are having the number of moles of hydrochloric acid that is in excess, and then these are number of moles of what? Of hydrochloric what? Acid that reacted with what? Yes, the number of moles of what? Of hydrochloric acid reacted with what? With what? Calcium carbonate, right? Then the total here will be what? Will be 1.6. I think I'm getting 1.6 here. Mole per cubic what? Per cubic decimeter, right? So that is the concentration of what? Of hydrochloric what? Acid. Ne? All right. So let's check another question here. Maybe before we move to another one, I want to check something here. All right. So here we are having 50, right? Cubic decimeters dilute hydrochloric acid of the unknown what? Concentration. Then the excess is neutralized with what? 25 cubic centimeters of sodium hydroxide solution that they prepared. Ne? So I want to check something here. Okay, yeah, so I think this is what we're supposed to do. Then let's look at the second what? Question. It's another structured what? Question here. So the conductivity of 3 acid solutions. So there's a question here. Good afternoon, say, will we be needed to calculate the pH of a substance? Okay, if yes, how do we determine it without a calculator? I don't know what is NBTS. Oh, you mean the NBT test, ne? No, I don't think so. I don't think so. Because for you to be able to calculate the pH, right, you need a calculator. So you cannot use your head to calculate the negative log of something, right? So I don't think it will be there. All right. Okay. Then another question here. The conductivity of 3 acid solutions, A, B, and C, as shown, is investigated at the same water temperature. So we are having A, B, C. So A, it's 0.1 mole per cubic decimeter, right? And then of hydrochloric sulfuric acid, it's nitric acid of the same concentration, and ethanoic acid of what, of the same what concentration. But what we know that is that this one is strong acid, this one is also what, a strong what, acid, but this one would be what, a weak what, acid. Ne? Right, so strong, weak, strong. But and again, another thing here, this one is diprotic, this one is monoprotic, and then this one is also what, monoprotic. So you're having a diprotic strong acid, monoprotic strong acid, and monoprotic what, weak acid. Ne? So here the question is about conductivity. The brightness of the bulb in the apparatus shown below is used as the measure of the conductivity of what, of the solutions. Right. Now, what is important here, learners, is that remember this is a strong acid, a strong acid. So strong acid, they ionize completely in water to produce high concentration of what, of hydronium what, hydronium ions. Weak acid, they ionize in completely in water to produce what, low concentration of what, of hydronium what, ions. Ne? Then but now you are having a strong strong diprotic acid and a strong monoprotic what, acid. Then when you look at those two, it means that it will have high concentration of hydronium ions, right? And then a monoprotic will have a low concentration of what, of hydronium ions compared to a diprotic strong acid. So a diprotic strong acid contains high concentration of hydronium ions compared to a monoprotic what, strong acid, right? But a weak acid ionizes incompletely in water to produce what, low concentration of what, of hydronium what, ions. Then if we look at the conductivity, A actually will have high conductivity than B, right? Why A will have high electrical conductivity than B, although both of them, they are strong acids. But the first one is a diprotic. So if it is a diprotic, obvious, it means that it can donate more than one proton, right? So obvious that solution will contain high concentration of hydrogen ions or hydronium ions compared to a nitric acid, which is a monoprotic. So the conductivity of A will be higher than the conductivity of what, of B. Why? Although both of them, they're having the same concentration, but a diprotic contains a high concentration of hydronium ions compared to a monoprotic what, acid. Then if you can look at B and C, both of them, they are monoprotic, but B is strong acid, C it's a what, it's a weak acid. So a strong acid, they ionize completely. So still, if you look at B and C, B will have high concentration of hydronium ions compared to what, to C, but A will have high concentration than B and what, and C, because it is a diprotic what is this diprotic strong what, acid. Then the brightness of the bulb for each of the solution is compared. In which solution, A or B, will the bulb be brighter? Give a reason for the answer by referring to the types of acids. So A or B, obviously we are expecting the bulb to be brighter in what, in solution A, if you are using solution A. Give a reason, right, by referring to the acids, right? So although both of them, they are strong acids, but A is a strong diprotic acid. So obviously it contains what, a high concentration of hydronium what, ions. So A is a strong diprotic acid. It contains high concentration of hydronium what, ions. I hope you understood that. So why are we choosing A instead of B while both of them, they're strong acids? Is that A is a diprotic acid, or a strong diprotic what, acid. 7.1.3, in which solutions, B or C, will the bulb be brighter? in which solution, B or C? So now they're comparing what? Strong acid with a weak acid. So you're expecting the solution to be brighter if you're using solution B. Why solution B? B is a strong acid. B is a strong acid. Strong acid. So it ionizes completely in water to form high concentration of hydronium ions. So B is a strong acid, so it ionizes completely in water to form high concentration of hydronium ions. Ne? Then we have answered 2 questions on electrical conductivity. I hope learners you understood why we are choosing A compared to B, right? It's because A, it's a strong diprotic acid, so it contains high concentration of hydronium ions than a monoprotic one, right? Why are we choosing B instead of C? B is a strong acid, right? C is a weak acid. B ionizes completely in water to form high concentration of hydronium ions. Ne? Then, a hydrochloric acid solution, HCl, is standardized by titrating it against 25 cubic centimeters of 0.04 mole per cubic decimeter of sodium carbonate solution. Then at the end point, so what is end point? I hope you still remember we did titration, or what steps that you need to follow when you're performing titration, right? So end point, that is the point where the indicator changes color. So you cannot do or cannot perform titration without adding a suitable indicator, which will determine what the end point, right? So end point, that is the point where the indicator changes color. Then it is found that 19.5 cubic centimeters of hydrochloric acid has what reacted. Okay, it has what reacted. Okay, then the balance equation for the reaction is sodium carbonate plus HCl to produce sodium chloride plus carbon dioxide and water. So calculate the concentration of hydrochloric acid. Okay, so maybe before we calculate the concentration of hydrochloric acid, let's just check what is given for hydrochloric acid. Hydrochloric acid is standardized by titrating it against what? 25 cubic centimeters of, so for sodium carbonate, ne? For sodium carbonate, we have what concentration and the volume, right? Then at the end point, it is found that 19.5 cubic centimeters of hydrochloric acid has what reacted, ne? So it's only 19 at the end point that has what reacted. So they want us to calculate the concentration of the hydrochloric acid. So one of the things that we can do here, because this is complete neutralization, we can use this equation CA VA over CB VB equals to NA over NB, right? So where you have concentration of an acid, it's what we are looking for. Then volume of an acid, it was found that at the end point it was 19.5, so it's 19.5. So there's no need for me to convert here because volume VA, VB, both of them, they're in cubic centimeters, so they will cancel out the units. Then concentration of a base 0.04 times the volume of a base, which is what, 25. Then Na, number of moles of an acid. From the balance equation you can see the coefficient is what, is 2. And the number of moles of a base, from the balance equation you can see the coefficient is what, it's 1. Then cross multiplication, right? So cross multiplication, I'm having concentration of an acid, right, is 2 into 0.04 times 25, right, over what, 19.5. So I'm having 2, before that is 0.04 times 25, okay, times what, times 2, which is going to be what, 2 over 19.5. 2 divided by 19.5. So the concentration here is 0.1013 mole per cubic watt decimeter, or 0.10. Okay, so or what we can do, we can calculate the number of moles of a base. So number of moles of a base, it would be CV from N, C equals to N over V. Concentration 0.04 times what? 0.025. We don't have a choice here. We have to convert cubic centimeters to cubic decimeters. So I'm having 0.04 times 0.025. Ne? So which is what? 0.001. These are number of moles of what? Of sodium what? Carbonate. Ratio of sodium carbonate to what? To hydrochloric acid. It's 1 is to what? Is to 2, which is 0.001 is to what? Is to x. Ne? So we multiply this by 2. Right? So the number of moles, it's 0.002 mole of what? Of HCl. Ne? Then concentration is equal to N over V, which is 0.002 divided by 0.0195. Ne? Divide by 0.0195. I think must get the same answer, yes, which is 0.103 or 10 if you round off it to two decimal places, mole per cubic watt decimeter. So this is what we are supposed to do, actually, to calculate the concentration of what? Of hydrochloric what? Acid. Ne? So this is what you're supposed to do to calculate the concentration of hydrochloric acid. You can use CA over CP Vp equals to Na over Nb, then get the concentration. Then, or you can calculate the number of moles of the base, use mole ratio to get the number of moles of hydrochloric acid, then calculate the concentration of hydrochloric acid using C equals to N over V. N is 0.02. Then the volume that neutralized 25 cubic centimeters of sodium carbonate, it was 0.0195 or 19.5 cubic watt decimeters. Right. So I hope we are still fine. Then we have calculated the concentration, right? Then suppose a few drops of water were present in the burette before it was filled with hydrochloric what? Acid. So here we are performing titration. So suppose a few drops of water were present in the burette, right? So I hope you saw the burette last week, and your teachers should show you and its function, right? So before it was filled with hydrochloric acid solution, how will the volume of hydrochloric solution needed to reach the end point be affected? So there are few drops of water, all right? So which means that if there are few drops of water, right, in the burette, okay, so what will happen to the volume of hydrochloric acid solution? We're expecting the volume of the hydrochloric acid solution to be what? To be greater, okay? So how will the volume of hydrochloric acid solution needed to reach the end point be what? Be affected, all right? So then it will be greater, because when you add water, right, what happens to the volume? What happens to the volume of the solution? The volume of the solution will what? Will increase. Okay. Volume of a solution what? Will increase. Okay. So give a reason for your answer. Right. We have answered 7.1.2, 7.1.3. Right. So give a reason. So this one is sorted. We got it right. So it should be greater than, right? Then you can see, so it's what I wanted to show you here, right? The volume will be greater than, right? So this, we are adding water. So when you add water, it's like when it comes to dilution, when you add water to a solution, what happens to the volume of that solution? The volume increases, okay? So if the volume increases, right, what happens to the solution? The solution becomes dilute, okay? the solution becomes dilute because we are increasing what the volume of what of that solution. So a few drops of water will dilute what the hydrochloric what acid. Therefore, greater volume of acid would be needed to neutralize what the base. Okay, so we are adding water, volume increases, so it should be greater. So because those drops of water will dilute what the solution of hydrochloric acid, therefore a greater volume of acid will be needed to neutralize what the base. Okay, then another question. So here you can even see here they used both options there. The option 1 was this one, and then the option 2 was that one, calculating the number of moles of a base, move from there, find the number of moles of an acid, and then from there get the concentration of what of an acid. So both options were used, okay, or both methods were used. Right, last question. A concentrated household product, ChemClean, contains ammonia as the main cleaning agent, right? To determine the amount of ammonia present in 1 cubic decimeter of ChemClean, the following procedure is followed, right? So then 20 cubic centimeters, right, of ChemClean is added to what, to 250 cubic centimeters flask, ne? So here we are having what 20 cubic centimeters, right, of ChemClean is added to 250 cubic centimeters flask, ne? Then the flask is then filled to the 250 cubic centimeters water, sorry, mark with distilled water. Okay, so this is what they've done, right? Then the diluted solution is titrated against the hydrochloric acid solution of the concentration as calculated in question 7.2.1. So already we know the concentration of hydrochloric acid, which is what, 0.1 mole per cubic decimeter. So 20 cubic centimeters of clean, this is 20 cubic centimeters of clean, right, is added to 250 cubic centimeters flask, right? So here we have 20 of ChemClean, which contains ammonia, right? The flask is then filled to the 250 mark with distilled water. So it's filled, you can see that. So, but remember, we are having 20 cubic centimeters of ChemClean, right? And then filled to what? So in other words, water that was added here, or the volume of water that was added here, it's what? Is 230 cubic centimeters to make the solution of 250 cubic decimeters of dilute ChemClean. Hope you are following, ne? So there was 20 of ChemClean, and then they've added water, and then they filled actually the volumetric flasks to that 250 mark. But if it's 250, if this volumetric flask is 250 cubic centimeters, how much water was added, or the volume of water that was added is 230, because 230 plus 20 gives us what, 250 cubic centimeters of the dilute ChemClean. Okay, then what are they saying here? The dilute solution, this dilute solution, right, is titrated against the hydrochloric acid solution of the concentration calculated in question 7.2.1. Okay, 1. Do we know the concentration of this solution? No, right? How can we calculate the concentration of what, of this solution? Okay, so you are having what, 20 cubic centimeters, right? And then from 20 to what now, to 250. Okay, then what are we looking for here? We are looking for the concentration. We can get the concentration of what, of this dilute ChemClean. Okay, so how can we get that? This is dilution here. All right, hence here they're saying what, dilute ChemClean. And for dilution you can use C1 V1 equals to what, C2 V2, right? So here they are saying the concentrated household product ChemClean contains ammonia as the main cleaning agent. That, to determine the amount of ammonia present in 1 cubic decimeter of ChemClean, the following procedure was followed. So we have 20 cubic centimeters, right? Okay. Then of ChemClean is added to 250 cubic centimeters of this, right? Then the flask is filled to that. Then let's check, because there's missing information here, right? During the titration, 22 cubic centimeters of the diluted ChemClean solution is neutralized by 18.7 cubic centimeters of hydrochloric acid solution. The balance equation is this one, right? Then what are they looking for here? Calculate the mass of ammonia in 1 cubic decimeter of ChemClean. All right. So where are we going to start here? We have what the volume of hydrochloric acid. We also have the concentration of hydrochloric acid, which is 0.1 mole per cubic decimeter. So we can get the number of moles of of hydrochloric acid. Then from number of moles of hydrochloric acid, then we can get the number of moles of of ammonia, right? So this is what they've done here, right? You can see these are the number of moles of hydrochloric acid, which is what I was trying to say here. We can get the number of moles of hydrochloric acid, N equals to CV. The concentration, it's the concentration that we calculated, right? Which is 0.1. And then you have 18.7 volume, which is the volume of hydrochloric acid, which is 18.7 times 10 to the power negative 3. Why is it times 10 to the power negative 3? They are converting cubic centimeters to cubic decimeters. So these are number of moles of hydrochloric acid, right? Then from number of moles of hydrochloric acid, we are looking for what now? The number of moles of ammonia that reacted. And how we're going to get the number of moles of ammonia reacted? We have to use the mole ratio. Okay, so mole ratio, if you check in that equation, the ratio is 1:1. Ammonia to to hydrochloric acid, the ratio is 1:1. Hence the number of moles of ammonia reacted is also 1.87 times 10 to the power negative 3 mole. Okay, so now we have the number of moles of ammonia that reacted. So actually these are number of moles of ammonia in 22 cubic centimeters of ammonia. So the number of moles of ammonia in 22 cubic centimeters, it's 1.87 times 10 to the power negative 3 mole, right? Then now let's get the number of moles of ammonia in 250. Okay, so the number of moles of ammonia in 250 will be 1.87 times 10 to the power negative 3 times times 250. Okay, divide by by 22, and then those number of moles is 0.021 0.021 mole. Okay, then to get the initial number of moles, the initial number of moles, right? So the initial number of moles, which is, remember that 20 cubic centimeters of ChemClean, right? That was the initial volume. All right. So it's here. It's 0.021 mole. Okay. Then from here calculate the mass. All right. So when you calculate the mass is number of moles times number of moles is is mass over molar mass, right? Then the mass will be number of moles times times the molar mass, right? So here we're having 0.021, right, equals to m over over 17. Where is this 17 coming from? So the 17 is coming from ammonia, the molar mass of ammonia. Nitrogen is 14, and then hydrogen is 1. Obviously it will be 1 times 3 because it's NH3. Then here we are having what is this? We are having 0.357 grams, right? So we have 0.357 grams in 20 cubic centimeters, right? So we have 0.357 0.357 grams in 20 cubic centimeters. But in 1000, where is this 1000 coming from? The question says, calculate the mass of ammonia in 1 cubic decimeter, right? So, but in 20 cubic decimeters, we have what 0.357 grams in 20 cubic centimeters, and then obvious in 1000 or in 1 cubic decimeters, you will have what 0.357 times 1000 divided by 20 to get what 17.85 grams, right? So what is 17.85 grams? Okay, so the correct answer here is what? It's 17.85, right? So these are some of the questions, learners, that you should get. So these are not just easy questions, and this is fortunate that you started this in grade 11, which means that moving forward, even next year, you will do more of these questions when it comes to what your acids and what and bases. So, but I think we have noticed something when it comes to these equations, you move backwards from bottom to top for you to be able to get these questions. So these questions, actually, they need a lot of understanding. Understand the statement, what is happening, and it's not something that you will understand in one day. So you should keep on practicing these questions. Actually, these are stoichiometric what? These are complex stoichiometric what calculations that you need to look at. So you cannot run away from them. Even next day they will be there. So hence you need to make sure that you understand your stoichiometry, which is, it's nice because you did stoichiometry in grade 10. You also did stoichiometry in term 3, grade 11. So you shouldn't struggle that much to do these stoichiometric what calculations. So the last question here: will the pH of the solution at the end of the titration be greater than equals to or less than 7? All right. So then they're saying what? Motivate your answer by writing down the relevant equation. Okay. So is it going to be what greater than 7, equals to 7, or less than 7? So here you have ammonia, which is a weak base. This is a strong what? Acid. Ne? So it's a titration of a strong acid and a weak base, right? So you're expecting the salt solution that will be produced. So actually what should be produced here? It should be ammonium what? Chloride. So in other words, they're asking you, is ammonium chloride acidic, basic, or what, or neutral, right? So this one will be what? Will be acidic, right? So it should be what? Acidic. Why am I saying it's acidic, right? So to support your answer, one, what you need to do, you write dissociation for that salt, which is NH4Cl, to produce what? NH4 plus what here? Cl what? Minus. Remember, this ion is from HCl, which is a strong what? Acid. This is from a base, a weak base, which is ammonia, right? So remember, no hydrolysis for this one. Then we have to write hydrolysis for ammonium ion, right? Hydrolysis, it's a reaction of what? Of salt with what? With water. So it will be what? NH4 plus H2O. What will be produced here is NH3 plus what? H3O what? Plus. Okay? So where is this NH3 plus H3O plus coming from? Remember, you had ammonia, which is what? A base. And this base will produce what? A conjugate acid. Remember, a conjugate acid, it's a substance formed after a base has gained what? A proton. So we add a proton to a base to produce a conjugate what? Acid. So this comes as an acid. Obvious, it will be a proton donor. Then this will be what? A conjugate what? Base. Okay, so hence here this has lost a proton or has donated a proton to what? To H2O, right? So you can see one of the products there is hydronium what? Ions, right? So it means that if there is high concentration of hydronium ions, right? So the pH of this solution should be what? Less than what? 7. And if the pH is less than 7, it means that the solution here will be what? Will be acidic. So what is the question? Will the pH of the solution at the end of the titration be greater than 7, equals to 7, or less than 7? So it should be less than what? 7. And then write down the relevant equation as motivation for the answer, right? So the relevant equation here, they are looking for what? The hydrolysis what? Reaction. So hydrolysis, remember, is for ions from what? From a weak base, or ions from what? From a weak acid. So this ammonium ion is from a weak base, then there will be what? Hydrolysis from what? For that base, right? Or for that ion to produce what? Ammonia plus hydronium what? Ions. So the reaction shows that there's high concentration of hydronium ions in that solution. Then it means that the pH will be what? Less than 7. And if the pH is less than 7, therefore the solution should be what? Acidic. So these are some of the questions that we'll get. So keep on practicing them. Even next year, grade 11, we are still going to focus on questions, the multiple choice questions, and also the structured questions under acids and what? And bases. So I think for today we have done enough. Thank you so much. So see you next week. So next week we are going to focus on our redox what? Reaction. So the focus will be redox what? Reactions. Thank you so much for attending or for watching this lesson. I hope you learned something, and moving forward, please make sure that you watch these lessons, because they are very, helpful for most of the learners, right? And actually for your final exams, because you're about to write your final exams. So please make sure that you don't miss our lessons. Thank you so much, and enjoy the rest of the day.